Good morning, my YouTube viewers. Crystal here. I wanted to make you a quick video before I have to leave my flat. Basically, I decided that I wasn't going to do a blog post on how PCA was used with the with the E. coli data set because it didn't work. And so because it didn't work, I thought, well, what's the point in making a blog post? Although I like to do a blog post every day or something like that. So I decided to use PCA. That's, what does PCA stand for? Let me just look and see what PCA stands for. I don't remember a lot of the time. I'm just looking on another window. It's a principal component analysis, so that's what it stands for, principal component analysis. I thought, well, I'll check it out on the Titanic site because that's what I wanted to check anyway, was the Titanic site. And I wanted to see what happened when we employed PCA on the Titanic site. So the first thing I'll tell you is my notebook is open. My notebook is sharing, so you can go into my notebook and look at it and see what it says. And I'm sure you can see the public score right here, but I'm not going to tell you the public score until the very end because I've got some things to say about that. So the first thing we'll do is we'll talk about the problem statement of the Titanic data set. And this is a Kaggle competition question. So the sinking of the Titanic is one of the most infamous shipwrecks in history. On April 15, 1912, during her maiden voyage, the widely considered unsinkable RMS Titanic sank after colliding with an iceberg. Unfortunately, there weren't enough lifeboats for everyone on board, resulting in the death of 1,502 out of 24 passengers and crew. While there was some element of luck involved in surviving, it seems some groups of people were more likely to survive than others. In this challenge, we ask you to build a predictive model that answers the question, what sorts of people were more likely to survive, using the passenger data, i.e. name, age, gender, socioeconomic class, etc. Well, I can tell you right now, it's the women and the children who were the ones who were more likely to survive. But what I wanted to do is I wanted to employ the PCA. That's the, what are we calling it? The principal component analysis. So the first thing that we did was we loaded up our libraries. We imported the libraries that are already installed on the Kaggle Jupyter Notebook. And then we loaded up our files. So you can see that these are the files that are already present in the Kaggle system. And now what we've done is we read our files. We read the train file and we read the test file. So the train file is what we're going to train and validate on, and the test file is what we're going to test on. And now what I had to do was I had to impute any null values, and so I just replaced any null values with the most commonly used value because we had a problem with the Titanic data set. With the Titanic data set, some of the columns are numeric and some of the columns are categorical, and because of that, it was hard for me to use an iterative imputer, and also couldn't use the column transformer in this particular competition question scenario because I wasn't sure exactly how to use the column transformer with PCA. So I just replaced everything with the mode. So we've done a graphical analysis of our target, so you can see that more people didn't survive than did survive. So now what we've done is we've processed our data. So what we did was we took all of the object files and we ordinal encoded them to give them a numeric representation. And in addition to that, any of the files that were ordinal encoded that needed to be made integers, we made them integers as well. So the age, we made that an integer, and the fair, we made that an integer too, because I just felt that it was just cluttering up the prediction. If you said, oh well, I'm 7 3/4, so I just made it an integer so it would round it to an 8, or it would clutter up the prediction if you said, well, my fare was 99 pounds 99 cents. It would just round it up to 100 pounds. So that's what I did. I made the age and the fare integers just for simplicity to help out. And what I did was I ordinal encoded both the train and the test sets. So now what I've done is I've set up my X, Y, and X test values. Y is train survived. X is train drop, passenger ID, survived, name, cabin ticket. X test is drop, passenger ID, name, cabin ticket. Because this is just really, I didn't include the titles in this one because this is just really a simple program to try to employ PCA to see what would happen if I used PCA. Okay, so we split the X file up for X file, the X data set up for training and testing. So X train, X val, Y train, Y val equals train test split, X file, X, Y, train size equals 10, random state equals 1, stratify equals yes, shuffle equals true. So train, shape, and then we tested the shapes of X train, X val, X, Y, X val, and X test. And so all of these data sets had 7 columns except for the Y's. So now what we did was we put it on a scaler, because the only way that the PCA is going to work is if all of the values are in the same range. So we use the standard scaler to put all the values in the same range. So scalar equals standard scalar fit X train, and then X train equals scalar transform X train, X val equals scalar transform X val, and X test equals scalar transform X test, because you're only supposed to fit on the X train and you're supposed to transform everything else. So what we did was we set up our class weights, and this is a formula to help you set up your class weights to balance them. And now what we've done is we've applied our PCA, which is your principal component analysis. So PCA equals PCA in components equals 6. Now I tried every variation. I tried 2, 3, 4, 5, 6, and 6 is the one that gave me the highest accuracy on the validation set. So I stuck with 6. Principal component analysis is supposed to take higher dimension data, and it's supposed to break it down into lower dimensions, and then you sacrifice a little bit of accuracy by doing that. So normally this piece of data would have 7 dimensions, but I broke it down to 6 dimensions because the 6 dimensions is what gave me the higher accuracy. And they say that because PCA reduces the dimensions, it kind of speeds everything up, so it's supposed to improve the accuracy. So X train equals PCS dot fit transform X train, X val equals PCA dot transform X val, X test equals PCA dot transform X test. So now what we do is we set up the explained variance. So this gives you the explained variance of the PCA. Now what we've done is we've defined our model, and we just use ADA boost classifier on that. And because we're using PCA, we had an accuracy of 96.88, which was less, the accuracy was less than if we hadn't employed PCA. But we tested on our validation set, and on our validation set we had an accuracy of 78.89%, which was higher than an accuracy that you would get not employing PCA, because I checked. If you didn't employ PCA, then the accuracy that you would get on your validation set would be like 77.78%. And then with PCA, we've got a 78.89%. So our accuracy improved 1% on the validation set. So that meant that it was like tuning up the X data set a little bit more, X-train really. So we predicted on our test set. And we have no way of knowing what the answer was because Kaggle's got that information. And we put it in a data frame. We submitted it, put it in a data frame. But what I wanted to do was, while I was in this data frame, what I wanted to do is I wanted to do a visualize the PCA. So we set up PCA again, and then we standard scaled the X, because earlier in the program we standard scaled the X train, but now what we want to do is we want to standard scale the X. So X equals standard scalar fit transform X. So now what we do is we look at the mean and the standard deviation. So your mean is -7.97 to the 18th, and your standard deviation is 1. And then what we do is we set up our features columns. We've got 7 features columns. And the features column is for each column. We normalize the data. Normalize equals PD data frame X columns equals features columns. So now our data is normalized. And now what we do is we employ PCA again, but in this instance we have n components equals 2 because we want to make this two-dimensional data. So you can see that what we have with PCA, the 2 columns for principal component 1 and principal component 2. And now what we do is we print explain variation per principal component. Number 1 is 29.5%, number 2 is 24.35%. And now what we do is we make our graph. We plot the principal component 1 and principal component 2, and we plot this on, and I said E. coli. I shouldn't have said E. coli. I should have said Titanic. So I'll go back and change that. And so this is it. This is our graph. So because of the graph is the way it's set up, it's going to be very difficult to get 100% accuracy, because you got all of the ones interspersed in there with the zeros. So 0 didn't survive and 1 is survived. But since you got the ones and the zeros mixed in with each other, it's going to be very difficult to get 100%. The only people who get 100% are the people who actually go in and research the Titanic. And when they research the Titanic, they research who survived and who died, and they write their program to that effect. But that's like overfitting, and you're not supposed to do that. You're supposed to just use the standard model. So it's going to be really difficult unless I go in and do some serious programming, it's going to be really difficult for me to get 100% because you got all the ones mixed in there with zeros, and it's difficult for the computer to pick this out. And whenever I submitted my file to Kaggle, I got a 71.78%. So that meant that I lost about six points in accuracy. And that's what PCA does. PCA reduces the dimensions, and then you have a less accuracy. But what's unusual is I had a higher accuracy with the validation set, but I had a lower accuracy with the test set. So that's yes and no. Yes and no. Does it increase accuracy? Because in one instance it increased accuracy, in another instance it decreased accuracy. So that's about it for this video. I think I've talked about PCA and how I used it and the coding that I used. And you can see that this is sharing. So you're able to get into my Kaggle site. You're able to get in and look at my notebook if you want to. And that's it really. So if you like my video, please like, subscribe, and share. If you like the work I do and you want to make a donation, I've got my email address to my PayPal account in the description box down below. And thank you so much for watching this video, and I look forward to making more videos for you.